So let's say we have a linear system that can be represented in matrix vector form as AX equals B. Then the solutions here, will be some type of vectors. Let's call these vectors X equal U. Let's call them U. They're going to consist of what's called a particular part plus a homogeneous part. So here, P is the particular part of the solution, and VH is what we're going to call the homogeneous part. Of the solution. And the way this works is I can plug in U here in for X, and that'll work. So we get that A times U gives me B. But also when I plug in the particular part, P, I'll also get B. So the particular part of U works for AX equals B. Now the homogeneous part here, VH, is the one we're calling VH. When we plug VH in, let's call that yellow, that only works for the homogeneous equation. So when I take A times VH, that's going to give me back the zero vector. Yeah, so every solution to a matrix vector equation AX equals B is going to have a particular part and a homogeneous part. See if I can get this to right. So the particular part is the green part, and the homogeneous part is the yellow part. So we talked about that briefly. Let's actually go a step further and prove a theorem, state a theorem, and then prove it. So this is actually theorem 6, I believe, in your textbook. It says, suppose you have a matrix vector equation AX equals B that's consistent for some B. It doesn't have to be for every B, but just for some B. So let's say there's some B out there in Rm that this is consistent for. So suppose AX equals B is consistent for some B in Rm. That means AX equals B has a solution. And let's say X equals P, so X is unknown, but let's say X equals P is a particular solution, Then that means the set of all vectors of the form U in Rn, so all vectors U in Rn, such that A times U equals B, that is going to be equal to the set of vectors U in Rn, such that U is of the form P plus VH. So we know what P is already. P is a particular solution to AX equals B. But VH is going to be a solution to the homogeneous equation. So A times VH should be the zero vector, right? If VH is a solution to the homogeneous equation, then AVH should be the zero vector. So I want to show, what is this saying? This is saying, on the left here in blue, this is all the solutions, all the vectors U that you can plug in for X and get B. So this is saying all the solutions to the equation AX equals B. That's what blue is. All the solutions to the equation AX equals B. And on the right, this is saying all those vectors that have a particular part plus a homogeneous part. So remember, P is the particular solution to AX equals B. So it has a particular part plus a homogeneous part. So what this is saying essentially is that all solutions to AX equals B can be written in the form a particular part plus a homogeneous part. Now let's prove this, that these two sets are equal, the blue set and the red set. So I'm going to do a proof here. So in the background, we're assuming we're supposing that the matrix vector equation AX equals B is consistent, or we can say has a solution for some vector B in Rm. And so we know there's a solution because it's consistent. And we're going to let X equal P be a particular solution. Particular solution. Okay, well, what does that mean? If X equals P is a particular solution, X equals P is a particular solution. Well, that means we can plug in P here for X, and it'll give us an output of B. So that means thus, A times, instead of an X, I can replace that with the P, equals B. So I plug in P for X. So AP equals B. Okay, so now we want to show that these two sets are equal. We want to show that the blue set is contained in the red set, and then we want to show the red set is contained in the blue set. So I'm going to first we show that the blue set, all the vectors u and Rn, such that AU equals B, we're going to show that is contained within the red set. All the vectors u and Rn, such that u can be decomposed as a particular solution to the AX equals B equation plus a homogeneous solution to the homogeneous equation. So let's see if we can show that. So to show that the blue set is contained in the red set, I'm going to pick an arbitrary element in the blue set. So let's pick an arbitrary element in the blue set. Let's call it, I don't know, W. Let W be a vector in the set blue. So W is in the blue set. What does that mean? So W satisfies the form. It's in Rn, and A times W would have to be equal to B. So that would mean A times W, right? It has to be one of those U's. W is one of those U's. So A times W, it gets plugged in place of U, equals B. Okay, now I'm going to do a trick. I'm going to say let VH be, I'm going to define VH to be W minus P. I don't know if that's a good color. Maybe I should use green, but I don't know. Let VH be W minus P. Okay, we have a W, and we know what P is. P is this particular solution back here. So now I'm going to do another trick. I'm going to say note W equals P plus W minus P. Right? Isn't that correct? W is equal to P plus W minus P. We're talking about vectors here. Oh, wait a second. What's another name for W minus P? Well, it's VH. So I'm going to write here W here, which is equal to P plus W minus P. That is equal to, if I can get this to right, P plus, I'm going to replace this right here, W minus P, with VH. Right, that's what we had earlier, right? VH was W minus P. Now, let's see if VH truly is a solution to the homogeneous equation. Let's take VH and plug it in place of X in the homogeneous equation. So I'm going to take A, instead of times X, I'm going to put VH in place of where an X would go. So AVH. We want to see, is that equal to the zero vector? We want to determine, is that equal to 0 vector? Well, let's see. A times, let's see, VH. What is VH? It's W minus P, right? VH is W minus P. You can get this P red here. Now, using our properties of matrix vector multiplication, we can basically distribute this matrix A. We get AW minus AP. But wait a second, what is AW? What is AW? If you go back here, right here, right? AW is equal to B. So I'm going to replace AW with B. And minus, what is AP? What is AP? Well, remember back here, AP is equal to B. I'm going to replace that with a B. So I'm going to get a vector B minus a vector B is going to give you the 0 vector. So what do we have? We have A times VH equals a 0 vector. So that means VH is indeed a homogeneous part. A homogeneous part. It's a solution to the homogeneous equation, AX equals 0. Okay, so good stuff. So we can conclude here that thus W, since it's of the form P plus VH, where is that? That's right here, right? W is of the form P plus VH. And because A times VH equals a 0 vector, then we can conclude that W is an element of this red set, right? It's the set of all vectors in Rn such that the vector is a P plus a VH where A times VH equals 0. So W is an element of this red set. All those vectors in Rn such that U equals P plus VH and also AVH equals a 0 vector. Let me get this erase here. I got some circles I want to erase. Let's see if I can erase these circles. Good. So we started off with our green W in the blue set, and we ended up with W. Let's make it green. We ended up with W in the red set. So that shows that the blue set is contained in the red set. Now the goal is to show that these two sets are equal. So we also want to show that the red set is contained in the blue set. So let's say that next. So next, we show that the red set, that's the set of all vectors U and Rn, such that U equals P plus VH, where AVH equals a 0 vector. We want to show that set is contained in the set of all U and Rn such that AU equals B. So we're trying to show the red set is contained in the blue set. In other words, all those vectors that can be decomposed as a particular part plus a homogeneous part are solutions to the equation AX equals B. Now that's what we want to show here. So to show that the red set is contained in the blue set, I'm going to pick an arbitrary element in the red set. Let's call it W again. So let's let W be a vector in the set in the red set. All those vectors in Rn that can be decomposed as a particular part plus a homogeneous part Now, what does that mean if W is in that set? That means W can be written as a particular part plus a homogeneous part. So that means W is of the form P plus VH. Of course, A times VH is equal to 0 because VH is a homogeneous part, a solution to a homogeneous equation. I'll make VH black and I'll make P red. Let's do that. Now, I also want to show that W is a solution to the equation AX equals B. I want to show W is in the blue set, in other words. So let's see if we can get W to be in the blue set. So what I'm going to do, I'm going to take A. I'm going to try to plug in W right here where the U's are. Let's plug in W there. So I plug in W and I get what? A times, so in place of W I can put what? P plus VH. And that's going to give me what? AP plus AVH. Now, what's AP? Do you remember what AP is? If you go back at the very beginning, right here, right, we said that AP is equal to B. So this right here is equal to B. Also, my question is, what's AVH? Well, AVH, remember, is the zero vector, so we can replace AVH with the zero vector. Now, what's B vector plus the zero vector? That's the B vector. So if you look closely, we have AW equals the B vector, right? AW equals the B vector. So that means W is in this blue set. Thus, therefore, W, I guess W is green right now. W is an element of this blue set right here. The blue set is all the solutions to the equation AX equals B. So the set of all vectors U and Rn such that AU equals B. And that's it. We have shown that the red set is contained in the blue set. So we showed the blue sets in the red set and the red sets in the blue set. Let me do a little erasing these highlighting boxes and stuff. So we can finally conclude that therefore, or hence, if I can get this to write, this thing. Hence, these two sets are equal. The red set, which consists of all those vectors in Rn, with a particular part plus a homogeneous part, are equal to the set of vectors U and Rn that themselves are solution to the equation AU equals B. That's it. That's the proof. I'll put a little box to indicate we're done. Yeah, so all this is saying is that solutions to AX equals B can be decomposed into a particular solution part plus a homogeneous